Hello learners, welcome to the next session. In this session, we are going to discuss about noise and medication techniques in noise and medication techniques in quantum computing. Quantum states are highly sensitive to their environment, so definitely we may have an interaction with outside world like heat, vibration, and electromagnetic field. So this can definitely disturb the quantum state, leading to many kind of errors during computation and measurement. So noise is one of the biggest challenge in quantum computing. So we can have to think about the quantum states required for computation. So here we are going to discuss about the noise types and effects and what are the techniques we can go with that kind of errors. So noise refers to unwanted disturbance that alert the state of the qubits during computation. These computation can raise from environmental factor and hardware impurification or interaction between the qubits. Noise leads to errors such as decoherence, that is loss of quantum information, and gate error, incorrect operations. So what are the different kind of noise? Bit flip errors, flip errors, and depolarization errors. So in the bit flip errors, the qubit states are to be changed to ket 0 to ket 1. So that is called as vice versa. So modeled by applying an X gate with uncertain probability. So n times of mm, probability, which is equal to 1 minus s of probability plus s times of x probability and x, where s is the error probability here. And the phase flip errors, the phase of the qubit changes mapping to ket 1 to ket minus 1. So modeling with the help of Z gate, this is also to be represented with the help of S times of Z probability and Z. Next is depolarizing noise. Qubits loses its quantum information and becomes mixed state. So that is also represented here 1 minus S of probability plus S divided by 3, and X probability of X plus Y probability of Y plus Z probability of Z. So this type of errors has to be reduced with the help of strategies, different kind of strategies. So the first one is protocol based bully channel categorization. Here we are going to use that Clifford gates to estimate average noise behavior. With the help of state preparation measurement and gate errors are to be decomposed to model a noise at varying the circuit's depth. So the effectiveness is reduced output error by 88%. The next is quantum NAS, noise adaptive search, a framework that identifies noise parameterized quantum circuits by training super circuits to evaluate candidate architecture. So here we can easily think about the low impact gate to reduce the noise source. And the main effectiveness here, we can think about the quantum chemistry task also, reduced computation overhead by 5 to 10 times compared to the brute force search methods. Third is hybrid error mitigation. Here we can combine the multiple techniques, noise estimation circuits, iterative Bayesian unfolding methods, randomized coupling, and zero noise exploration. Any methods are also to be used. Mainly it is used in IBM quantum device for chemistry simulation. And the next one is amplitude damping noise method. Here we are using quantum um, receiver computings to calculate the noise computation. And the fifth one is dynamic error suppression, and real-time application we can go with FPGA based applications. And the sixth one is probabilistic error cancellation, anti-noise method also to be applied to by using pre-categorized noise models. So here we have simple code. First, create a simple circuit with the state of ket 1. So quantum circuit and measure the values. Define a noise model, bit flip error with the probability of 0.2, and run the simulation with noise. So with the noise, we are going with AER simulated platform, and job noise, and the result of the noise also to be printed, and run the simulation without noise with the help of execute QC backend, and shots are to be applied. And next, the plot the result. The results is ready to represent that value to be measured with or without noise. This color, the first one is to indicate that with noise information, and the next one is without noise, that is idle information. The blue bar is all measured return one values, and the red with the noise is also to be due to the flip-flop noise. Some of the measurements return zero, simulating the real hardware errors. So this is about the error to be created in the quantum computing environment due to the environmental factors, and these are the steps we can solve this error to calculate the error computation and remove the errors with a different kind of techniques. Thank you, learners.